Good afternoon, everybody. You can hear me, I suppose.
Yes, ma'am.
Yeah. So briefly, I'll just take you to what we had studied in the previous class. Okay, we are in chapter number 26, which is on electric fields. Okay, and we have used two words frequently. Then one was the source charge and the test charge. Source charge is the source of the electric field, and test charge is the charge that you use for measuring this unknown field. And then we saw the relationship between them. E is equal to limit Q naught tends to 0 F by Q naught, where F is the uh, force experienced by Q naught when it is in the field of Q. Okay. Now we wrote this equation for a point charge, but remember this equation holds good even for extended or continuous charge distributions, or even combination of point charges giving rise to discrete collection of charges or continuous charge distribution. In the last chapter, for example, we have seen continuous charge distributions like a uniform line charge. Then we have seen a ring. Then we have seen a uniformly charged disk. Then we have seen a sphere, a shell. Okay, these are all continuous charge distributions. So even if your source Q happens to be a continuous charge distribution, this equation will hold good. And another thing that you should additionally remember is that the electric field will be parallel to the force if Q naught is positive. The next thing is Q naught. We have been calling it a test charge, but then it need not be a test charge. It can be any point charge. It can be any point charge. Okay. So with this in mind, let us just go to today's part of the lecture. Okay. So now from one single charge, we were talking about Q as a 1 point charge. So from there, let us move to two discrete charges, Q and minus Q, separated by a distance d. And this entity is called an electric dipole. I'm sure you must have heard this word electric dipole. Where did you hear that? Anyone? Anyone has heard this term electric dipole? No one? Yeah, where did you hear it? Have you heard this in chemistry? Dipole. Water is dipole. Have you not heard that? If you're going to be silent, I'm also going to be silent. Let me wait. I have no problem. Have you heard this, or say that you have not heard? That's it. Well, if it's a competition, then today I'm muting myself. I am also going to wait for 15 minutes. So you heard it. And Ranjini madam talked about dipole in the first two classes. She told me that. She told me that she's talked about dipole in the first two classes, and nobody seems to remember that. Okay, so remember, certain molecules behave like ammonia, H2O, HCl, and NaCl in the vapor state. In the vapor state, what happens is you will have Na plus and Cl minus. So all these things actually can behave like dipoles. What is the meaning of a dipole? A dipole is when, see, remember, if any molecule is going to have some positive protons and negative electrons, on the whole, it is neutral. Okay. Now just imagine that if you have your positive charge cloud and if it is spherical, and if you have your negative cloud also spherical, okay, then what happens is the center of both these will coincide. The center of both these will coincide, and on the whole, this is a neutral entity. On the whole, this is a neutral entity. But then in certain type of molecules, what happens is the center of the positive and negative cloud don't coincide. Like for example, H2O. H2O, if I am going to ask you to draw, you will show your oxygen, then you show your hydrogen here, one hydrogen, the other hydrogen. Anyone remembers this angle? What is this angle? What is this angle between the two hydrogen atoms? This bond angle. What's happening? Let me see who are all the people in the class. Maruti, can someone tell me what is this angle
90.
between the hydrogen? Huh? 90?
90.
90? Anyone
180,
else?
180
degrees.
100?
108.
108. Yeah, it's
104.
108. Yeah, that's almost correct. 107 point something. Okay, point something degrees. Okay, and because of this angle, you know what happens is the oxygen part of this molecule gets a small negative charge, and this hydrogen, the two hydrogens, have a small positive charge. So it's as if, you know, the entire thing is neutral, but then it's as if the negative and the positive part of this molecule are slightly displaced from each other. And what happens is they behave like what is called a dipole, and dipole shows some very interesting properties. Like, for example, your water, it's a universal solvent for many things. It can dissolve polar materials. It's able to dissolve only because it is a polar solvent. Okay, so like this, there are so many interesting properties that dipoles will exhibit. So here in physics, we are not going to talk about these angles and all that. We will treat any molecule which behaves as if it is a minus q and a plus q, a minus q and a plus q separated by a distance d. A plus q and a minus q separated by a distance d. So this entire thing is a molecule, okay? And we have to define what is called the dipole moment. We have to define what is called the dipole moment of a dipole. Dipole moment is defined, is given by the symbol P. It's a vector and it is equal to Q into D. Q into D, where D is a separation between the positive and the negative. And if you look at the D vector is going to have this direction. This is your D vector direction from negative to positive. From negative to positive. Therefore, your dipole moment vector also will have the same direction. Can someone tell me what will be the unit? What is the unit of charge? What is the unit of charge?
Coulomb.
Coulomb.
Meter.
Yeah, coulomb meter. D is meter, so coulomb meter. So that's the unit of dipole moment. It's a vector. Okay. So now what you're going to see is, though the dipole, this dipole molecule by itself is totally neutral, but then because of that small separation between positive and the negative cloud, they show some interesting properties. They become a source of electric field. Till now, you know that a charge can be a source of electric field, but then this also becomes a source of electric field, though it's neutral as an whole. Okay, so let's see what will be the electric field due to a dipole. So what we will do here is we will take a dipole and let the axis of the dipole be the z-axis. Let the axis of the dipole be z-axis. Let the midpoint be the origin. Let the midpoint be the origin. This is the axis. Okay. Now what we do is we consider the perpendicular bisector. The perpendicular bisector. Okay. And on the perpendicular bisector is your x-axis. On the perpendicular bisector, consider a point P. Consider a point P on the perpendicular bisector, which is at a distance x from the axis, which is at a distance x from the axis. So this total distance is d. This total distance is going to be d. So what will this distance be? What will this distance be? No, what will, no, just tell in terms of it, just d. So this will be d by 2. Similarly, this distance also will be d by 2. Okay. Now what we'll do is, we have taken a point P. Let the line joining the positive and the negative charge to the point P make an angle theta with the axis. So this angle is theta, this angle is also theta. So you can clearly see that this x-axis is a symmetric axis. What is above that is similar to what is below that. So there is some kind of a symmetry. Fine. Now what we'll do is, we have to find out what is the field at the point P. So what we'll do is, we will use the principle of superposition. We will use the principle of superposition. So using the principle of superposition, the net field E at that point, E at the point P, is going to be the vector sum of E plus plus E minus. E plus plus E minus, where E plus is the field at the point P because of the positive charge, and E minus is the field at the point P because of the negative charge. Okay. Here I'm going to use, instead of writing 1 by 4 pi epsilon naught, I'm going to put a K. So what will be the electric field at a distance R? So this distance is R, this distance is also R. What will be the electric field due to a point charge? You know, electric field due to a point charge is 1 by 4 pi epsilon naught Q by R squared. So we are just going to use this. Instead of 1 by 4 pi epsilon naught, we are just going to write K. Is that clear? So that's how you get this. And you see that the electric field to the negative charge also is going to have the same magnitude. First, I'm writing the magnitude. So no minus, don't put any minus and plus and all that. It is just KQ by R squared, KQ by R squared. Both are having the same magnitude. But then we are supposed to do a vector addition, So now let us visualize how these two vectors are going to look. Now I have my positive charge. The electric field at the point P due to a positive charge. Yesterday, what did we see? Electric field will be radially in or out for a positive charge?
Out.
Out. Radially out. So this is going to be the electric field, direction of the electric field because of the positive charge. And when it comes to the negative charge, we have seen that from the point P, it will be in. It will be towards the source charge. So this is your E minus. I hope this is clear to you, why this is this direction and this is going to be this direction. Next, we are going to now add these two vectors. Both of them have the same magnitude. So it's just adding to, so by now, so many such forces we have added in the previous chapter also. Now you're just going to add field, that's all. Okay, so if you add them, if this angle is going to be theta, okay, and then additionally you also know that R square is going to be equal to X square plus D by 2 whole square. So this is coming from Pythagoras theorem. Okay. Now let's now quickly look at if this angle is going to be theta. If this angle made by R with the perpendicular bisector with the axis is theta, then you can show that this angle also will be theta. This angle also will be theta. Similarly, this will be alternate angle. So this also is going to be theta. Okay, so now you're going to add two vectors having same magnitude and there is a symmetry. So the symmetry axis is going to be this. Symmetry axis is this. So very quickly you will be able to tell me that there will be this component and this component which will cancel out, So you're just left with only 2 times this component. So what is this component? Look at this right angle triangle and look at this arrow as the hypotenuse. So what will this be? This is going to be, I'm sorry, this component is going to be
Cos.
Cos. It's going to be cos. Okay, therefore, and 2 times because each of them will be contributing E cos theta. So 2 times E cos theta. So we'll put it as 2 1 by 4 pi epsilon naught Q by X square plus D by 2 whole square and cos theta. And you look at this, suddenly we have put a minus sign here. Why did we put a minus sign here? Anyone?
It is in the negative X
Why did we put this? Right. It is along the negative Z direction. Our positive Z direction is this. So it is along the negative Z direction. So you put a minus. And next thing is, what is my cos theta? What is cos theta from this triangle you see here? From this right angle triangle, what is cos theta? Cos theta will be D by 2 divided by under root of X square plus D by 2 square. Okay, so just put that here and then multiply. So when you multiply, what are you going to get? You get minus 2k q d by 2, and here you already have x square plus d by 2 whole square, and then you have an under root of the same expression. Therefore, you can just write it as under root of x square plus d by 2 square, the whole thing to the power of 3. Whole thing to the power of 3. Okay, and now look at this. This 2 and this 2 will cancel out. These two, both the 2's will cancel out. And what is your QD? What is QD?
Dipole.
Q minutes. That's your dipole moment. Therefore, you're going to get E is equal to minus 1 by 4 pi epsilon naught P divided by, you can either write it as R to the power of 3 or you can write it as under root of x square plus D by 2 whole square to the power of 3. Okay. And what we will now do here is, you look at the field direction. You're finding that E due to the dipole is anti-parallel to your P vector. The electric field due to a dipole is anti-parallel to the P vector. One thing, when I'm doing this, do you feel a sense of deja vu? You've seen it somewhere. Do you feel like that? Anyone here? Somewhere in the previous chapter, we've discussed something like this. Anyone remembers? You will remember only if you study, otherwise how will you remember? Do you remember we had a discussion on a line charge, half of it is positive, the other half is negative. Do you remember?
Yes, ma'am.
What is the charge Q naught? And we found that the force is in this direction. There also you had a similar figure like this. Okay, if you remember this, you will find that instead of a line of positive charges and a negative, here you're just having one positive charge and a negative charge. And instead of placing a charge Q naught at the point P, here you don't have anything. You're just finding what is the field. That's all. Otherwise, it's just the same. Otherwise, it's just the same. Okay. And what you realize is that you have seen these things. There's nothing new here. So the electric field, so that means you can conclude that a dipole can be a source of an electric field and it will create an electric field which is opposite in direction to the dipole moment. Next, we are talking about a molecule. So we're talking about molecule. What would be the sizes that what would be the value of D? Anyone? Can you guess what would be the value of D? I'm not asking you the numerical value. I'm just asking you the order of magnitude. D will be of what order? You are all chemistry students. You should be able to tell me this. What is the radius of a nucleus? Anyone? That you can't escape. Radius of a nucleus. Last time we discussed. In the last chapter. It's very sad. Nobody studied. What's the radius of a nucleus? Well, hereafter I will not ask you anything. I'll just keep lecturing. The radius of a nucleus is 10 to the power of minus 15 meters. And this D value will be more than that, of course, because we are talking about a molecule. But then it is just going to be of the order of around 10 to the power of minus 12 meters, which is femtometer. But your X is outside the molecule. Your X is outside the molecule. X may be a few centimeters or a few millimeters. But femto is very, very small when compared to X. Or for all practical purpose, you can assume that X is much, much greater than D. You can assume that X is much, much greater than D. Okay, so now what happens to this equation when X is much, much greater than D? Okay, for that, I just worked out here one step. So just take this P, so minus P by 4 pi epsilon naught. Take out your X cube from here. Take out your X cube from here. When you take out your X cube, what will you get? You will get under root of 1 plus D by 2Z whole square whole to the power of 3 is what you will get. Okay. And then let us do a binomial expansion for that. So when you do a binomial expansion, this is what. For this, when you do a binomial expansion, this is what you will get. This is what you will get. As such, you said X is much, much greater than D. So here we have X square is much, 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 much greater than D square for the second term. So the second term itself you can neglect. You can neglect. Therefore, this is just going to be equal to 1, or you're just going to get electric field is equal to minus P by 4 pi epsilon naught X cube, or the electric field is proportional to 1 by cube of the distance. Electric field is proportional to 1 by cube of the distance for a dipole. For a point charge, how is the electric field changing with distance? For a point charge?
It is inversely proportional to x square.
X squared, square of the distance. Whereas for a dipole, it falls off as 1 by x cubed. See, these are all very interesting relationships. If you just remember it this way, studying for an examination is going to be easy. And not only that, this also means one thing. If I have a point charge, the electric field does not become zero for a longer distance. For a longer distance, the electric field is not going to become, because it is 1 by r square. But when you're talking about dipole, it is 1 by x cubed. So very quickly, it falls to zero. So that means the electric field is non-zero for a very, very small region. Okay? So it's a very localized electric field when you're talking about a dipole. So now what I want you to do is, just, we took on the perpendicular bisector, we took a point and did the calculation. Now what I want you to do is, I want you to find out what is the expression for the electric field along the axis. Along the axis, now I want you to work it out. Please cooperate with me, work it out. Along the axis, consider a point P and find out what is the electric field at that point. So tell me, how should we do that? Let's use the principle of superposition again. Principle of superposition. From the principle of superposition, I will say that electric field at the point P is equal to electric field because of the plus charge plus electric field because of the negative charge. Okay. Now at the point P, can you put E plus? In which direction will E plus be? With respect to this figure, how do I put an arrow at the point P for the positive charge?
Away from plus q.
Away from plus q. So radially out. So away. So this is going to be E plus. Okay. And for the negative one?
Radially inward.
Inward. Radially inward. Now, can you say that both of them will be equal and cancel out?
No, ma'am.
No, because the distances are different. The distances are different. And I'm going to call this distance from this perpendicular bisector. Okay, from here, the midpoint here, from here, I will say that this distance is going to be equal to x. I will call this distance as x. Okay, so now what is going to be E plus? Magnitude of E plus is going to be? At what distance is E plus? The positive charge from the point P.
X minus
K
d by 2.
by, x minus d by 2 whole square. And similarly, your E minus will be x plus d by 2. X plus d by 2. So it's going to be k q by x plus d by 2 whole square. Next, I'm going to take, because I'm going to call this as my z-axis. So this is my z-axis. So positive, I'm going to take it as what is coming, the arrow in the upward direction, I'm going to take it as positive, arrow in the downward direction, I'm going to take it as negative. So let me just use that. Then my electric field is now going to be equal to kq by x minus d by 2 whole square minus kq by x plus d by 2 whole square. Which will dominate? Which will dominate? So finally, the electric field will be in which direction, up or down?
Upwards.
So look at the denominator and tell me whether E plus is going to be greater or E minus is going to be greater. Denominator is smaller here. Denominator is larger here. So tell me. KQ divided by smaller denominator. A smaller denominator is always going to be a larger number. So you can say that the net field is going to be in the upward direction. The net field is going to be in the upward direction. So let's just do the calculation and see. So that's going to be KQ and then 1 by x minus d by 2 whole square minus 1 by x plus d by 2 whole square. Okay, so I can just write it as KQ. And then here I will take the LCM, so therefore it becomes x minus d by 2 whole square, x plus d by 2 whole square. And then in the numerator, what am I going to get? I'm going to get x plus d by 2 whole square minus x minus d by 2 whole square. Okay, then what happens after that? After that, what happens? I just have to open the bracket, that's all. So open the bracket. Therefore, the electric field is going to be equal to kq, then here x square minus x square, then d by 2 square, d by 2 square will get cancelled out. Then what will I have? I will have a 2, it won't be 2. So I will get a 2 dx. Will I get a 2 dx if I expand this and then do an addition? So I'll get 2 dx divided by x minus d by 2 whole square into x plus d by 2 whole square. Please, I'm not doing anything great there. I'm just using a plus b whole square, a minus b whole square. That's all. So just expand, open up, cancel out whatever is common with minus signs, and then do the rest of it. You're going to get this. Okay, so when I complete it, I should finally get, and what is kk is 1 by 4 pi epsilon naught, and there is a 2 there, so it becomes 1 by 2 pi epsilon naught, and here q into d is going to be p. Okay, then you have an x divided by x to the power of 4 for x much greater than d. Okay, for x much greater than d. And remember here, my P and E will be parallel to each other because my electric field vector and my P vector are going to be parallel. So there is no minus sign there. Once more, I'm going to see that the electric field is falling off as 1 by cube of the distance. What was given in the book was on a perpendicular bisector, you took a point. Now, along the axis, you've taken a point. So for both of them, you're finding that electric field falls off as 1 by x cube. Okay, now in chemistry, there is also another entity that you must have heard about that is called a quadrupole. Have you heard of quadrupole? Anyone? Quadrupole? Looks like you people have never heard of anything. What is a new movie that got released this week on your platforms? OTT? Anyone? Any good movie that you want to recommend for me? Oh, that also you can't do. Shucks. Okay, forget it if you can't even do that. Yeah, so now what we have to do is, I would like you to work out this particular problem. So this is something that do it yourself. So this is do it yourself. Okay, so here what you need to do is you have to realize that we are having 2 dipoles. It's quad means 4. Okay, you are having one dipole here and you have another dipole here. And just now for a perpendicular bisector at some distance, what is the electric field we have seen? So what you have to do is, let us call this as the first dipole. Let's call this as a second dipole. Okay, and this distance is going to be x. So for one of the dipoles, this distance is going to be how much? Anyone? For this dipole, for the second dipole, what is this distance going to be?
X minus.
It's going to be x minus a. And for this dipole, the distance is going to be x plus a. So what you need to do is take along with sign, go to the previous problem. For a dipole, the plus and minus and all you have to see carefully, and then get what is going to be the dipole moment at this point P because of both of them, and then do an addition and get your answer. And you will find that the electric field is going to fall off as 1 by x to the power of 4, x to the power of 4 for x much greater than a, x much greater than a. Okay, and this also means that a quadrupole is something that is going to have a much more interesting relationship. It is a source of electric field, but then its electric field becomes zero very, very close to it. Very, very close to it. That means very, very localized region only. There is an electric field because of a quadrupole. Okay. So this, I want you to do it yourself. Now let's try this one. Okay. So this is also a quadrupole. This is also a quadrupole. I hope you're able to recognize that there are 4 charges here. So a plus Q, minus Q, minus Q, plus Q. So a quadrupole is, if you model it, no, it is a combination of 2 dipoles. In such a way they combine that the electric field does not become zero. Electric field will not vanish. Okay, I want to find out the electric field at the point P. So what do you do here? You have to use the second problem. What I did, no, along the axis I did a problem, remember? So take that problem. Take that problem and then look at that minus Q plus Q, that order you have to see, and then what is the field at the point P you take. Then do the vector sum and get the answer, and you should get electric field is again falling off as 1 by z to the power of 4. So do it yourself. So doing these things will give you some confidence. Okay, you can either do it this way, or you can treat it as simply 3 charges. You can treat it as 3 charges, Q, minus 2Q, and a plus Q, as 3 charges, and then apply the principle of superposition, taking into account the distance. Still you will get the same answer, because after all what we are doing is only just applying the principle of superposition. So I want you to do it yourself in your own interest. They may not ask you to do this entire thing in an examination, but then we can always ask you questions on how does it fall off with distance and things like that. So better work it out. Okay, now, so from a single point charge, we move to a dipole. From a dipole, we move to quadrupole. So now discrete charges. The quadrupole is a combination of 4 discrete charges. So from that, we are moving to continuous charge distribution. So just like we did in the case of forces, if this is my charged object and I am interested in finding out what is the field at some point here because of the charges here, let's say it is uniformly charged. Okay, so what should I do? Tell me. If it's uniformly charged, what should I first do? Please tell me. I have to divide this entire charge into small charge elements carrying charge dq, which can be written in the form of either lambda or sigma or rho, depending on whether it is a line charge, it's a surface charge, or a volume charge. So you should be able to write dq is equal to lambda into distance if it is line charge, dq equal to sigma into dA if it is surface charge, and dq equal to rho into dV if it is a volume charge. Okay, you have to just do that. And because of this point charge at a point P, first you write what is going to be the electric field. Call that electric field as dE. Then you want E, so E will be integral of dE. Do the integration. So does this remind you of something? Does this remind you of something?
Force on continuous charge distribution.
Force due to a continuous, not on, force due to a continuous charge distribution on a point charge Q0. Yes, it's the same thing. Wherever F was there, you put E, that's all. Wherever F is there, put E. Additionally, also remember what I just told you at the beginning of today's class, E is equal to F by Q0. Only this you have to do. So all same expressions, you just have to take the force expression for all the charge distributions and then divide by Q0, you will get your field. So I don't have to teach all that all over again. So let's just look through it. So we start off with a line charge distribution, uniform line charge distribution of length L. And then on the perpendicular bisector at a distance y, you have a point P. At the point P, we are not putting Q0. We want to find out the electric field at the point P. So what we can do here is, we can simply take the expression for the force. We can take the expression for the force and just divide by Q0. Take the expression for force and divide by Q naught, you will get your answer. But for your sake, I'm just showing only one such calculation. So let us take a charge element dq at a distance z. Okay, therefore dq will become equal to lambda into dz, and then this distance is r. Therefore, r will be equal to under root of y square plus z square. So just put that into this equation, okay, and then draw your arrow, dE arrow, because the electric field will be radially out. So this is your arrow. Now similarly, take a mirror element here. Okay, do the same. You will get a dE here. And then sum of these two. If you do, you're going to get this as your answer. Okay, the electric field will be away from the points, from the source. So line charge is your source and your electric field is away from the source. Okay, so this is the answer you're going to get. But I just tried to show one, but for the others, we need not do all this. But even before that, what we do is, we can see that the electric field, the net electric field is going to be, for a line charge, the electric field is going to be away, okay, and perpendicular to the line charge, away and perpendicular to the line charge. So keeping that in mind, let us just look at this line charge. So this is my line charge. So let's say my pen is my line charge, okay. If I draw a plane like this at the perpendicular bisector, why should I take a distance y like this? I can take a distance y like this. I can take a distance y like this. Here. I can take a distance y anywhere. Perpendicular bisector in any direction on this plane I can take. And at every point here, I find that the electric field is going to be away from the source. Away from my source. And at every point, I can actually draw an imaginary circle. I can draw an imaginary circle around this wire. And I find that at every point on that imaginary circle, the electric field is going to have the same value. The electric field is going to have the same value, or what I am getting here is called a cylindrical symmetry. Yeah, I've already written that. It is called a cylindrical symmetry. Okay, I can just imagine a cylinder. Instead of taking a point here, if I'm talking about a very long charge distribution, I can actually imagine a cylinder. And at all points on the cylinder, the electric field is going to have the same value on the surface of the cylinder, and it will be out, radially out. Okay, and what you get is called a cylindrical symmetry. Next thing is, let us look at what happens when y becomes much greater than L. So this was my line charge, this is my y, this was my L. So what happens when y becomes much greater than L? Remember what happens to F when y becomes much greater than L? We said that the charge placed here will not be able to see this as a line charge, it will see it as a point charge. So you should get the same thing here. Okay, next, let us see what happens if L tends to infinity. L tends to infinity. If L tends to infinity, it can be shown that the electric field is going to be 1 by 2 pi epsilon naught lambda L by y. Lambda L by y. When L tends to infinity. Or for a dipole, for a line charge. For a line charge, you're seeing that the electric field falls off as 1 by distance with a cylindrical symmetry. So now I hope you'll be remembering point charge 1 by r square. Then dipole 1 by r cube. Then for a quadrupole 1 by distance to the power of 4. For a line charge, it is 1 by y. Okay. Now let's go to the electric field due to a uniform ring of charge. I'm not going to do all those things once more. You just have to take the expression for the force. I've taken the expression for the force that you have derived in the previous chapter. And then if I want the electric field, what should I do? I should take this force equation and divide by Q naught. Just get rid of Q naught. Then I get my field. So what is the answer I'm getting? 1 by 4 pi epsilon naught Qz by under root of x square plus z square plus r square whole to the power of 3. Okay. Next, what happens if z tends to infinity? If z tends to infinity, or I shouldn't even say z tends to infinity, I'll say z becomes much greater than r. When Z becomes much, much greater than R, you can show that this point P will not be able to see this ring. It will be able to see this ring as a point charge. It will see it as a point charge. Therefore, the electric field equation is 1 by 4 pi epsilon naught Q by Z squared. Okay. And what happens when Z equal to 0? Look at this equation. And in this, you put Z equal to 0. Z equal to 0 means you are at the center of the ring. What is the field there? Field will be
0.
Force will be 0. If you put a charge Q naught there, force will be 0. Therefore, field also will be 0. And again, you can also do, after this, no, in the previous chapter, what I had done was I had taken a semicircle like this, and then at a point here, I asked you, I put a charge Q naught, and then asked you to find out what is going to be the force on it. Remember, instead of putting a point charge Q naught, I can simply say, find out what is the electric field at the point P. At the point P, what is the electric field? So that can be a question. So it's all the same. Wherever F is there, F equation don't have Q naught. That's all. Then you get your field. Okay. Next, let us go to the electric field due to a circular disk of uniform charge density. If it's a circular disk of uniform charge density, if I had placed a charge Q naught here, if I had put a charge Q naught here, then I would have got an expression for the force, and the expression for the force would have been this. If I want a field, what should I do? I should simply divide by Q naught, so this Q naught will go away, and I get this particular equation. And what is my sigma? Sigma is total charge on the plate divided by the area of the plate. If the plate has got a radius r, then it is Q by pi r square. So you got your expression. Next, what we do is, some interesting results will come now. Okay, next what you do is, what happens if Z becomes, I don't like this, I will say, Z becomes much, much greater than R. What happens if Z is much, much greater than R? When Z is much, much greater than R, okay? When Z becomes much, much greater than R, don't say it is Z divided by Z, therefore it is 1. No, you shouldn't do that. Take Z out of the denominator. Take Z square out of the denominator. When you take Z square out of the denominator, there is an under root, therefore it becomes a Z. It comes out as a Z. And here you have 1 plus R by Z whole square. Okay. Now this Z and the Z will cancel out. Both the Z's will cancel out. And then look at what you're going to get here. 1 plus R by Z when Z is much, much greater. Okay, for that, what you have to do is you just you come here, and instead of writing 1 by under root of 1 plus R by Z square, you just write it as, instead of this, you write it as 1 plus R by Z square whole thing to the power of minus half, and then do a binomial expansion. Do binomial expansion of this. So you get 1 minus 1 plus half R square by Z square. Okay, this plus 1 and minus 1 will get cancelled out. So you get finally the expression for the, here what I have done is I have multiply and divide by pi. This pi has come because I have simply multiplied and divided by pi. And then sigma into pi r square will be equal to, look at this, sigma into pi r square will be the total charge Q on the plates. Therefore, I get electric field as 1 by 4 pi epsilon naught Q by Z square. Q by Z square. And this is the expression for the field due to a point charge. So this is what happens when you're talking of a distance that is very, very large when compared to the radius of the plate, uniform charge distribution. Okay. Next, what we'll do is, let us look at what happens. We'll do the opposite. What is the opposite? What happens if your disk is going to be very, very large when compared to Z? That means you're going to consider a disk of uniform charge, and you're going to consider points very, very close to that disk. You're going to consider points very, very close to that disk. Last chapter when we did this, I gave you the example of Earth. Earth looks like a sphere from moon, it looks like a sphere. If you go to sun or outer space, you will see it as a dot. If you come towards the earth and come very close to the surface of the earth, it doesn't look like a sphere, it will look like a flat surface. It will look like a flat surface which is very, very big. You're not able to see the edges. So this third situation is like that. When R is much, much greater than Z, the point P will not be able to see the edges of this plate. It will see it as some infinitely large plate. Okay, and the expression for the electric field, this is a very, very important equation. The expression for the electric field will be E is equal to sigma by 2 epsilon naught. Sigma by 2 epsilon naught. You are not having R, you are not having Z in this particular equation. E equal to this you have to remember, you will be doing problems based on this. Electric field due to a uniformly charged sheet for points very close to the sheet. And remember, we are talking of insulators, charges are not moving. Okay, so the electric field is given by sigma by 2 epsilon naught. And as usual, electric field, so this plate, I'll just show it as a line here. If I'm seeing from the side, it will look like a line. It will look like a line. And the electric field will be away from the positive charge, And you will find that the electric field will be uniform. It will be uniform electric field and perpendicular to the surface. Uniform and perpendicular to the sheet of charges. And remember, this is only for points close to this sheet. When you consider a point P close to this sheet, then the point P doesn't see this as a circle or a square or anything. It sees it as an infinitely large playground. So it's not able to see the edges. Okay, and the electric field will be perpendicular and uniform. You take this point here, or you take another point, wherever you take, the electric field will be perpendicular and therefore uniform. If instead of a positive charged plate, if you had a negatively charged plate, then the electric field, can someone answer this? If you had a negatively charged plate, then what would have happened? Electric field will be? What will be the direction of electric field if it's a negatively charged plate?
Towards the surface.
Towards the surface. Please remember, from positive charge, electric field always goes out. To negative charges, it always comes in. That's the golden rule to know. Okay. Now, what I'll do is I'm going to stop. I took a class with a fever. I took a vaccination and I'm running a temperature. I didn't want to miss a class, so I just took a class today. Okay. So in the next class, what we'll do is we will see what is the electric field due to a shell. Then what is the electric field due to a uniform sphere of charge. A sphere and a shell, I hope you can differentiate. Shell is just like only one surface is there, inside is hollow. So what is the field due to that? The next is hard sphere. There is charge everywhere inside. Then what is the field? That also is going to be similar to how you did for force only. Just remove Q naught, F will become E. That's all. So we'll do this in the next class. And after that, what we'll be doing is we'll look at, so electric field itself is a concept that was artificially introduced. Why was electric field concept introduced? Someone can tell me to explain? To explain? Action at a distance. If you have two charges not touching each other, how are they influencing each other? To explain that, this concept of electric field was introduced. So next what we'll be doing is we will look at electric field and this abstract concept. We are going to put it on paper. We are going to see it as a drawing. That also can be done. So we are going to see electric field representation. So pictorial representation like a graph. Okay. So for various charge distributions, we'll see how the electric fields will look. Magnetic field, and you've studied in school, no? Like that. Electric field for various charge distributions, we'll see. Okay. So this is how the next class is going to go. Any doubt that you want to ask? Guys, any doubt? Have you people cared to take the material from the drive? Or see the material from the drive? Okay, if nobody is saying, then today I'm going to remove the material. I'm not going to save it there. Looks like you don't need it at all. It's a job for me every time saving it and sharing and all that. I don't have to do that. How many? 45 people are there in the class. 80 people should be there in the class. Akshara, do you want to use the slides or you don't want the slides?
Yes, ma'am.
Then why is it that nobody is even bothering to see it? If these slides are not looking good,
No, ma'am. They are
PDF I put, last chapter's PDF I have put already. I don't think anyone has even bothered to see. 25th chapter I completed. I put that PDF of that entire slide so that the entire thing you can see. You don't have to keep on switching the video and seeing the video every time. Video you can see whenever you have some doubt. So PDF has been shared. So please go through these materials. And if I find that you're not seeing it, then I don't see any point in wasting my time doing this. Have you all given the attendance?
yes, ma'am.
Yeah. Now they're asking us for the attendance. We have to submit it to them. Okay. So better enter your attendance. I don't have to tell you this every class. Please enter your attendance because the management is asking us. They want to know whether you fellows are attending because tomorrow we don't want parents coming and saying that, did you people take class? Conduct chesara? That should not happen. So that's the reason why we are asking for attendance. And if your attendance is very bad, we'll inform your parents that your kid is anyway not coming to class. So maybe the parent is not spending money for internet or something. We'll inform them. Sir, you're spending so much for the fee. Why are you not spending money for the internet? Please get some decent internet connection for your children. So that's what they plan to do this time. Okay, because last time one parent comes and says in the last minute, my son didn't write any exam. My son didn't attend any classes. Okay, so you people are actually responsible for these kind of things happening. So please attend and please attendance is going to be seen this time. That is the information that we have been given. So that's why we are asking you to record it. Okay, so good day then.
Ma'am,
Yeah, tell me.
ma'am, are we having scientific measurements class today?
Today, Friday anyway, it is not there, ma. You will have class only once a week. One class for physics, one class for chemistry.
Okay, ma'am. Thank
Friday,
you.
no class. And I think some of you are facing problem in uploading the PDF onto the LMS, right? Is that problem resolved?
Ma'am,
Yes,
actually, it
Huh?
was, we could, ma'am.
You couldn't do it. Huh? You go and
We
check.
could do it.
You could do it? Okay, fine. Then I
Yes.
don't know. Some students, they kept on messaging that they are not able to do it. So please don't.
After an half an hour of time later, I was able to upload it, ma'am.
So don't clog it. Just do it on time. Then you should be able to. See, yesterday there was a situation. I think there was some problem. So we also kind of look at it a little leniently only. But then this cannot happen every week. Okay, once in a while it's all right. So please don't wait for the last minute. You are given more than 24 hours to upload. 1.5 days you are getting. So please finish it and upload it. Okay, I think there is going to be a change in the timetable for the lab. This afternoon, evening lab is becoming so difficult for the students. So, did Lalita madam tell you anything about changing the timing of the lab?
No, ma'am.
So they're expecting a change of time so that you can have those classes in the morning. And plus, some students are also having this issue of, ma'am, 3 days we are getting 3 days in a week, all classes, we are getting tired and all that. So we are trying to shift this physics and chemistry lab to scientific measurements to Tuesday and Thursday. So anyway, madam is discussing with the coordinators. So she will tell you that. So till she tells you that, this is the time. Is it clear? We are trying to push it to Tuesday, Thursday, first hour. If we are able to, great. That way, in the evening, you will also not get totally bogged down by so many classes. Okay. So let's hope she will inform you if there is a change. Okay. Good day then.
Ma'am, should we join today? The
No, Friday, no class at all. Friday, no class at all.
Until information is given.
Unless and until some holiday comes, you missed, and then we have to compensate. Or chemistry madam calls you. Physics, no class on Friday. That is sure. Okay, that's what all of us have decided. So don't bother. We should be having classes on Tuesday and Thursday. That's what we have asked, and they are also technically agreed. So let us see. Once they say yes, then we can have it. I'm sure you will like that better, right?
Yes, ma'am. And if it is there, then it will be like chemistry, physics, and scientific measurement.
Oh, physics. So Tuesday and Thursday, that whatever it is, madam will inform you. That
Okay.
way in the evening, by 4:30 you are going to be free. You won't have anything after 4:30 if we do it that way.
Okay, ma'am.
We are trying that. So madam is the IC of the paper. So we take turns, different semesters, different people will be the instructor in charge. So this time madam is the instructor in charge. So she is supposed to officially communicate these things.
Okay,
Okay,
ma'am.
then.
Ma'am,
Okay.
and one last request, ma'am. Like, I mean, last time we had in the academic calendar, Holi was declared as holiday.
Hmm.
Then later, due to change in the academic calendar, it was removed. And
Yeah.
even for Good Friday, it is still even in the change timetable also, it was given as holiday.
Ah.
And then later, no one informed us. I mean, like, we haven't got any mail also from the college side.
Okay. What is my name?
Huh?
What is my
Elizabeth,
name?
ma'am.
Elizabeth. I am sitting here and taking a class.
Yes, ma'am.
Yeah. What is your name?
Naveen.
Naveen. So I'm sure Naveen will not have much of a problem with Good Friday.
No, I'm not saying that, ma'am. Like, we actually, I had a plan of going to my hometown today.
See,
But later,
no, the thing
Like-
is, you are expecting your teachers to get into administration where they are not supposed to.
I'm not telling, at least,
Care of
I mean,
it.
at least
Proper
you can put in a
instructions aren't
message,
given,
ma'am.
ma'am. That's it.
And the problem is talking to us is of no use. We can at most, it'll become a gossip. That's all. Nothing more than that. You should talk
Oh,
to
no,
them.
ma'am. Actually, yesterday when I was speaking
You
with
have a
Rakesh,
chairperson,
sir,
you have a chairperson for student affairs, right?
yes, ma'am, I mailed him. I got no reply till now.
No replies are given back, ma'am.
Hey, you can always call him, talk to him. You can always. That's not difficult. Do that.
Actually, I spoke with Rakesh sir yesterday. So, sir said that all the faculties have received a mail that there's no holiday tomorrow. So
Yes.
what I mean is, like, at least from your side, if you put in a group saying that tomorrow we have class, we would be at least prepared for it.
Okay. The reason why we have not done it is because it is an administrative decision. So they are communicating directly with you. So we should not come in between. That's the reason why we didn't do that.
Okay, ma'am. Okay, ma'am.
It's say, am I not available at all times of the night? Also, you people keep calling and don't type. All the three of us, for that matter, madam, sir,
Yes.
me, all of us, we promptly do respond. If we have not done this, it is because we should not overstep. That's the reason why we didn't do that.
Okay, ma'am.
Okay, just assume that somebody has already informed you.
Okay, ma'am. Okay.
Okay, I understand. I understand your problem perfectly, but also try to understand our. It's a very delicate issue, trying to like just now I made a mistake telling you about that their classes may be shifted to Tuesday and Thursday. That itself is wrong. I shouldn't do that. There is an IC that for this semester she is the boss of this course. But since we decided, I'm unofficially telling you. That's all.
Okay, ma'am.
Okay, so there are certain protocols that we cannot actually break, but then in future I will try to tell you people. Okay.
Okay, I understood, ma'am.
Yeah. Okay then. Good day.
Thank you, ma'am.